Hi everyone, my name is Khalil Milini. I'm a PhD candidate in computer science at UC San Diego. I'm going to present today our paper, Recursive Tree-Structured Self-Attention for Answer Sentence Selection. So first we're going to introduce the problem. So answer sentence selection, or AS2, is the task of predicting whether a candidate sentence S contains an answer to a given question Q. And the motivation behind our contribution is that syntactic structure is an important component of natural language text. Tree-structured models have been used in a wide range of tasks, including sentence similarity and sentiment analysis. So in this paper, we investigate whether tree structures are useful for AS2. We introduce the tree aggregation transformer, a novel recursive and tree-structured self-attention model for answer sentence selection. Our model forms two sentence embeddings, one for question and one for candidate sentence, in a bottom-up tree-structured fashion. As you see here in this candidate sentence, Marrakesh, the noun phrase, is then combined into a verb phrase, a prepositional phrase, and then to form the entire sentence embedding. So we define a token embedding in our tree aggregation transformer as the concatenation of a semantic embedding and a syntactic embedding. The semantic embedding is a projection of the token embedding from a given pre-trained language model, whereas the syntactic embedding contains information from part-of-speech tags, syntactic categories, and the level within the syntactic parse tree. The syntactic embedding is a sum of three learned embeddings. The first embedding represents the token's tag. So it's a part of speech tag if the token is a word, or a syntactic category if the token is a classification or a separator token. The second embedding represents tokens level within the tree, inherited from the head of the token's constituent span. Our recursive model allows to represent sentences with as many tree levels as the corresponding syntax tree has. The third embedding represents the position of a token within the constituent span. This position embedding puts the token within its span context, whereas the position embedding of the semantic or language model embedding puts the token within the context of the question sentence pair. We also introduce recursive self-attention in our model. We add just one layer of self-attention on top of the pre-trained transformer. This allows the model to reuse the same sets of parameters across each tree level instead of training new ones as in previous work. So each input sentence is represented in a tree-structured fashion using its constituency parse tree. We use our own pre-trained parser from EMNLP 2020 to produce the constituency parse trees before training. The constituent span is fed to the recursive self-attention as a matrix of token vectors. This matrix includes the embeddings of the words of the constituent span, preceded by a first, start of sentence embedding, and followed by an end of sentence embedding. The start of sentence embedding is a classification token if the span is part of the question, or a separator token if the span is part of the candidate sentence, as you can see in this example. The constituent span embedding is the output of the first token. The first token embedding obtains through the recursive self-attention an attention-weighted sum of all of the span's token embeddings. This creates a span-specific embedding, conscious of the entire question pair input as a result of the language model layers, but focused on the tokens of a span as a result of the recursive self-attention. To obtain an aggregate sentence embedding, we proceed by embedding from the deepest level of the tree to the root, as shown in this figure. The computations are done on the same two sets of self-attention parameters. To reduce training time, we compute the constituent span embedding one level at a time. For instance, in this example, we compute the the NP, VP, and BP groups at once when computing the span embeddings at tree level 2. We efficiently compute all span embeddings only once and keep all computed span embeddings as they will be used in the next level. Descendance embeddings is obtained from the first token output of the computation at the root of the tree. Finally, for prediction, we concatenate the aggregate embeddings for the question sentence input there. So we use two kinds of data sets. TrekQA and WikiQA are traditional benchmarks of AS2 and are formally written. Yahoo CQA and Semival come from Yahoo Answers and the Qatar Living online forums. Both questions and answers are written by users online. So we call these community question answering datasets or CQA datasets. The metrics that we use are standard metrics in answer sentence selection, and they are mean average precision or MAP, and mean reciprocal rank or MRR. Whereas MRR scores how early a first relevant answer appears in the candidate lists, MAP scores the order in which all candidate answers are listed for each question. We perform an ablation study by removing the syntactic embedding part of the input representation. In this experiment, we're quantifying the added value of the learned syntactic embeddings for span position, part of speech tags and syntactic categories, and tree levels. Across all AS2 datasets, we notice that there is an advantage to learning syntactic embeddings as the sum of MRR and MAP scores are higher for the variant that includes learned syntactic embeddings. The advantage is clear for QA datasets, suggesting that formal language tends to benefit more from learned syntactic information. We compare our model against 5 strong baselines, 3 of which are on this table for conciseness. We have here Tenda, which is a 2-step transfer and adapt method, regular self-attention, which is a self-attention layer fine-tuned over frozen BERT large embeddings, and direct fine-tuning, which is directly fine-tuning on a pre-trained language model. And finally, evidence memory, the neural Turing machine as memory controller. Also hidden from the table is JSAMN, which is the gated self-attention memory networks, but those are in the paper. Results on the TrekQA and WikiQA show that tree structures perform well in formally worded texts, set a new state of the art in both datasets. And the performance is robust and consistent across Roberta and BERT. BERT results are in the paper. For CQA datasets, we established a new state of the art in Semival 2015. We matched the MR in Semival 2017, while our model scores below the state of the art in Yahoo CQA and Semival 2016. So we wanted to investigate this mixed performance and our limitations in the CQA datasets. So do tree structures improve performance? To answer this question, we propose 3 probing tasks. And the first one is top constituent prediction. This task looks to predict the top constituent sequence of the question sentence pair, the sequence of syntactic categories immediately below the S or sentence syntactic category. Then there is a tree depth prediction. The tree depth is the number of hops from the root node of the syntax tree to the lowest level and leaf nodes. And the third is input length regression. This task investigates whether the embedding is aware of how many words it contains. In our probing experiment setup, we use a simple 2-layer MLP with activation, and we train 36 probing models for each of the 36 combinations of a probing task, a dataset, and a representation type. For the syntactic probing tasks, that means the first 2, our tree structured model achieves F1 scores 3 to 4 times higher for the datasets where it sets a new state of the art. For conciseness, we only show here the results of the top constituent prediction, but the results for tree depth prediction are in the paper. The results show that when the tree-structured representation successfully absorb the syntactic information we fed it, there is a consistent increase in performance in the answer send selection task, as confirmed by high correlation scores with MAP and MRR. These positive correlation scores suggest that tree depth and top constituent are information that increases performance in answer selection. In the input length probing experiment, we observed that the mean squared error MSE of the tree structured representations is consistently and significantly lower than the one of the sequential representation. So that's a good thing, except for Yahoo CQA, where there is a very low MSE for both representations. This shows that the recursion of our tree-structured AS2 model makes representations aware of the length of their question sentence pair, but the correlation values show that this information does not necessarily help in the AS2 tasks. Finally, as a conclusion, so we introduced the tree aggregation transformer, a novel recursive and tree-structured self-attention model for AS2. Our method establishes a new state-of-the-art intra-QA and wiki-QA benchmark data sets with only one additional self-attention layer. We have mixed performance in the CQA data sets where text is informal and longer. We propose 3 probing tasks to examine what our tree-structured representations learn and find that there is a strong correlation between a model's ability to absorb syntactic information and its ability to increase performance in AS2 tasks compared to baselines. So our work suggests that there is more work to be done for tree-structured representations to adapt to noisy user-generated text. Thank you for your attention, and we highly encourage you to check our other work in question answering at ACL 2021. Thank you.